Hello! Today I'm going to introduce you to a method of interplanetary trajectory analysis with flyby options. Here is some general nomenclature I will be referring to throughout this presentation. The method I will be introducing is simply a brute force method for comparing departure and arrival windows for interplanetary missions. This analysis is also referred to as pork chop plots. Normally, these plots only include a direct trajectory from planet A to planet B. In this method, I will show how to conduct a pseudo-full factorial computation of an Earth-Mars mission with Venus flyby considerations for missions between the years of 2020 and 2040. The purpose of this mission timeline is the expected increase in missions to Mars in upcoming decades. Planning these trajectories requires the analysis of time of flight, C3 or energy required, delta V, and flyby maneuvers to ensure an optimal trajectory has been chosen. A flyby is a maneuver that is performed where the spacecraft will save fuel by utilizing a planet's gravity to alter the path and speed of the spacecraft. For these maneuvers, we consider a relative inbound and outbound velocity of the spacecraft during the flyby, as well as the distance of the spacecraft to the surface of the planet to check if the flyby is feasible. The velocity is first considered to determine if the maneuver is a free flyby, where the inbound and outbound velocities are equal, requiring no output energy from the spacecraft to complete the maneuver. For this analysis, we will be considering powered flyby maneuvers for a relatively small delta V, which means at the time of the flyby, the spacecraft will perform a small burn, resulting in an additional change in the path and speed of the spacecraft. The second condition to check is the height of the spacecraft during the flyby. If it is too low or close to the planet's surface, the spacecraft would crash. Here is the algorithm for computing a general full factorial computation for an interplanetary trajectory to create a pork chop plot. The inputs are the desired planet 1 of departure, the arrival planet, notated as planet 3 since we will be considering a third planet as planet 2 for the flybys, and the windows of departure and arrival dates. First, after converting the dates to a Julian date, you calculate the time of flight. Second, you find the planetary state at that certain Julian date to get the R and V vectors of planet 1 at departure and R and V vectors of planet 3 at arrival. Next, you determine the position vectors at departure and arrival, which are just equal to the planet positions at the time you're analyzing. Next, you compute a Lambert solution for your R of departure and of arrival at that certain time of flight, and determine the velocity of the spacecraft at departure and arrival. Last, you calculate your C3 values for both departure and arrival. You can also calculate values like V infinity and delta V total of the mission. For flyby analysis, it requires a much more computationally expensive program to calculate the R and V vectors for each planetary state, as well as computing two Lambert solutions. With the information produced from the Lambert solutions, you're able to find the C3 of departure and arrival, periapsis altitude during the flyby, and delta V during the flyby. And for our analysis, we are considering planet 1 to be Earth, planet 2 to be Venus, and planet 3 to be Mars. A much more efficient way to reduce the contour plot data is to run the full factorial computation for a general pork chop plot twice, once for planet 1 to planet 2, and again for planet 2 to planet 3, where planet 1 is Earth, planet 2 is Venus, where the flyby is performed, and planet 3 is Mars. The velocity information generated from these full factorial computations are combined to create the pseudo-full factorial computation of an Earth-Mars trajectory with Venus flyby considerations. Here are some of the equations required to generate the flyby data required for the contour plot. The V infinity inbound and V infinity outbound are products of the Lambert solutions found from the full factorial computation. Mu P is the gravitational constant of the flyby planet, and Rm is the minimum distance the spacecraft can approach to the planet's surface to complete a successful flyby. The change in velocity is then developed from these pre- and post-periapsis trajectories. For this analysis, an upper bound on the delta V of a powered flyby maneuver can be less than or equal to 0.3 kilometers per second. To combine the data of direct and flyby trajectories, it requires a different comparison than C3 values, since this would produce an unfair bias towards the direct trajectories, as flyby trajectories also include a delta V of the powered flyby maneuver. To account for this, one would calculate an integrated delta V total as a more uniform comparison for both trajectory types. The first part of the delta V total equation is the delta V of departure. This assumes that the spacecraft starts in a circular parking orbit around planet 1 or Earth with a radius equal to the departure hyperbola. Next, in this situation, we are going to ignore the delta V of arrival by assuming an error capture of the spacecraft upon arrival to planet 3 or Mars. Taking the delta V of the power flyby maneuver developed on slide 9, we are able to find the total delta V. Here is the resulting pork chop plot for an Earth, Venus, Mars mission from 2020 to 2040. Analyzed in MATLAB, this program took 70 hours to analyze direct trajectories and 140 hours to compute flyby trajectories. For this plot, it was limited to a delta V total of 4.8 kilometers per second, which these values were derived from the equation shown on the previous slide. The center of each contour area is considered to be a feasible launch opportunity based on a few feasibility conditions. The following conditions must be met in order for a flyby to be considered feasible. These numbers were taken from NASA JPL for what they consider to be a feasible mission to Mars, with an increased range for C3 of arrival and C3 of departure to account for improvements in technology that may take place during this 20-year mission analysis. The C3 for Earth departure must be less than or equal to 30 kilometers squared per second squared, and the C3 for arrival at Mars must be less than or equal to 40 kilometers squared per second squared. The height of the spacecraft at Venus encounter must be greater than 250 kilometers, and the delta V for the power flyby maneuver must be less than or equal to 0.3 kilometers per second. The next consideration is how to compare these feasible launch windows that meet the requirements overviewed on the previous slide. To do this, researchers determined the competitiveness of each opportunities by two criteria. If two neighboring opportunities have an overlapping departure date and one has an earlier arrival date, then the one with the later arrival date is considered to be dominated, since a shorter time of flight is desirable for missions. If an opportunity does not have neighbors with overlapping departure or arrival dates, the opportunity is not dominated and considered competitive. For this time frame, there were 6 feasible trajectories that included a Venus flyby out of 28 total feasible trajectories. This table shows all 28 trajectories the researchers deemed feasible for the 2020 to 2040 launch window. The highlighted rows represent the 6 flyby trajectories. It is interesting to note that the C3 of departure and C3 of arrival for the flyby trajectories are on the higher end of possible values. It makes sense that these would be higher for flybys because the delta V of the powered flyby maneuver must be taken into account. On the other hand, the reported delta V total for the flyby trajectories are on the same scale as the other non-flyby missions. This is because we used an integrated total delta V equation that converted the C3 of departure to a comparable value for the additional delta V every flyby trajectory would include. Here is the reference to the MIT Open Access article that did a great job at explaining this method of interplanetary trajectory analysis with flyby considerations. Thank you.